Hello, Mr. Ryan, are you right? Yeah, okay, so, yeah, we talked about the binary tree before, yeah? Binary tree. Binary tree. What's binary tree? Anybody?
It's,
Look, this is a binary tree. Okay?
tree.
Tree with what? How do we define a binary tree? Why this is a binary tree? Come on, question.
Because, yeah.
I know you know binary tree, but what is a binary tree? If you want to tell your friend what's a binary tree in computer science data structure, how would you describe it?
It's a tree with numbers in a certain way.
That's one answer, yeah, but it doesn't have to be numbers, right? I put a number just for the simplicity. It could be the names, it could be objects, it could be anything, right?
It could be me.
Yeah. Eric is object.
It
So,
could
okay,
be
so
playing games. Oh, yeah.
yeah. So listen, yeah, the binary tree is the data structure. What's the data structure? Data structure is
The data
to
structure.
is for computer. Is in computers. How do we store data? Yeah, we use the data structure. This is binary tree. Why is that? Because if you look upside down, it's like a tree, and binary means two. Means that for any node, the maximum number of kids is two. That's binary. Binary two, right? The binary tree is also it's a tree. Tree is a graph, right? Especially for binary tree, right? It has the maximum two kids, and the node without any kids we call it root. The node without any children we call it leaves. Okay, so in this binary tree, what node are the leaves? How many leaves nodes do we have here?
1, 2,
The leaf nodes. Come on.
3.
What's leaf? You said the.
Kids. 6, 7.
Okay, so why do you say 1, 2, 3?
Because there's 3.
Oh, you mean 1, 2, 3? You're counting 1, 2, 3. Okay, so you say 1, 2, 3. Okay, so 6, 7, 8. Alright. And how many roots?
And I thought you asked me how many are there.
I see. How many nodes root?
1.
Yeah, 1. Okay. And the nodes in the middle, they could be parents and the children. Okay. So we are given this binary tree, and each node it has this unique number. Okay, unique distinct number, right? Unique. So every node is different, and we are also given a target, k, right? For example, k equals 3. Okay, so can you tell me which is the closest leaf node to k equals 3? Which leaf node is the closest to node 3?
7.
Yeah, obviously. And how about if I give you 6? That's a tricky one, right?
6.
This is a very ambiguous. What happens if we already given the node, which itself is a leaf node? Should we return itself or should we find another leaf, right?
I think you should return itself.
Return itself?
Yes, because
Closest leaf node. Okay, so return the very nearest leaf node to the target k. So what happens if the target is already a leaf node? Right, so we just return itself. Yes, you're right.
yes,
We
bigger.
just return itself. For example, for simplicity, we are given this one node tree, right? It's the root. It's also a leaf. Okay, so we return 6. And how about if I have these 5? If I give you k equals 5, so which node is the closest node, leaf node to 5?
8.
8. If I have another leaf node here, like 9, and then I give you k equals 4, so which leaf node is the closest to 4?
8.
How about 9?
Uh,
Okay, you're measuring. Okay, this is not.
Wait, look.
I
It's
see.
A bit more.
Okay, good.
And this is that, and this is a bit
I
more.
see. Okay. Very creative.
Wow.
Okay, so in this case, you can return 8 or 9. It doesn't matter. We are not measuring the actual distance. Okay. Good. Yeah.
I'll
Okay.
return it.
Yeah. Either will be okay. Okay. What's your thoughts about this? We are
My
finding.
thoughts is looking at all of the
Yeah.
leaf nodes.
Yeah.
I just find all of the leaf nodes.
Yeah.
8, 9, 7 in this case.
And then
And then,
just calculate the distance to it.
yeah.
Okay, that's a very intuitive way. That's very good. Very good.
Intuitive is now the way for smart.
Intuitive is for human. We look at this. We have a very powerful brain. We can look at it. We can get the answer straight away. Because it's you just
depending on how big is your brain.
yeah, it's just there, right? But for
Yeah,
computer,
right.
the computers are dumb, right? So we have to tell the computer how do we solve this problem. Your approach is okay for humans. You know, if you ask mommy, look at it like that, it'll be very easy for mommy to figure out which is the closest leaf to the K. But if we implement this kind of idea in a computer, if you ask computer to do this kind of thing, then you'll be complex. It'll be difficult for computer to do it, right? Because we have to, implement this algorithm. It's not trivial to implement. We are given the root, right? We are given this root. According to your algorithm, find the leaf. To find the leaves, we need to do the depth search or breadth search, right? Yeah?
Yes.
And find the leaf. And then if we get a collection of the leaves, then we have to calculate the distance. Calculate the distance for all the leaves to the K, right? And also we need to find out the K. Where is the K, right? So in order to do this, it's not easy. How do we calculate the distance between two nodes in a binary tree? For binary tree, the tricky part is that once you are given the root, you can visit the kid from the parent. But you cannot go vice versa. In order to do that, we can convert it to a graph. Remember we talked about this, right? So the root children, yeah, left and right, right? It has 2 pointers pointing the left and right. But we want to visit the reverse direction. If we are given this root 2, we want to be able to reference the parent. So in this case, we convert it into a graph. Right? Yeah. Suppose we already have this kind of graph, and then we calculate distance between any two nodes. What's the traverser algorithm if we want to traverse a graph and find the shortest distance?
Breadth search, depth search?
Which one? Breadth search or depth search?
Breadth search.
Exactly. Breadth search level by level. When we found a node, it's the shortest distance, right? Yeah? Because look, it's breadth search level by level. When we found it, it's the shortest. Depth search may not be the shortest distance. In this graph, we are given this the unique numbers. Yeah. So first of all, convert the graph. Yeah. So step 0, convert the tree to the graph. Graph, we can use adjacent metric or adjacent list. Yeah, we talk about that. How do we store the graph, right? Graph is more like a G. G is a very powerful. Graph is a very powerful data structure with the it's a collection of vertex and edges. Yeah, vertex and edges. The vertex, edges, and for the graph, we can have these directed acyclic graph with the direction. Or if we don't have directions, we call it undirected graph. For the graph, you can have cycles in it, right? You can have different components in it. But for the tree, it has to be one piece, yeah, one component. You can't put the two trees. That would be called a forest, right? And you cannot have cycles. Yeah, the tree does not have cycles. Yeah, but it means that we can convert the tree to a graph, but not vice versa. Right? Sometimes the graph is not a tree, so that's why we cannot convert it backwards. But for definite tree is a graph, so we can convert the tree to a graph. To convert a tree to a graph, we can use the depth search, breadth search as well, right? So once we convert this graph, then we can do this. Eric, this is the improvement to your algorithm. You are saying that find the leaves, right? Find the leaves, do the breadth search each, right? And calculate the distance, right?
Yeah.
So why not start with this K and do the breadth search until it hits one of the leaves? It'll be quicker, right? Because in this case, I just have to do one thing, one breadth search, right? Make sense? So I do this breadth search. Yeah, 5, 6, 2. And then the next one, A. Okay, I found it. A is the shortest distance. But according to your algorithm, how do you do it? I do this breadth search here. Distance to here, 2. Okay, I note it down 2. 9, distance to here, 2. Here, distance 1, 2, 3, 4. 4. So I have to do 3 times of breadth search in order to find the shortest distance, right? And if we reverse it, if we start breadth search from the source, we hit the leaves and we stop. That's the closest.
Maybe.
Yeah, my approach is better, right? But yours is good, yeah, as a first try, okay? Correct me if you spot any mistake, okay? I cannot guarantee the code I write on whiteboard is 100% correct.
Which makes a smart level drop.
Okay, like G
G equals
default
graph.
dictionary, the default type is the list. We use the adjacent list. Adjacent list means that G, for example, G1 is a list 2, 3. It means that no one connects to 2 and no one connects to 3. Okay, that's what it actually means. Okay, so So we use the depth search. Define depth search. Depth search is quicker to write than the breadth search when we're traversing just the graph or converting the tree to the graph. So in order to do this, we need to have a parameter root, the current node, and its parent. When we traverse the tree, because it's depth search, from the root, we can find out its parent, right? So we can just add backwards a link, right? So look, if not root, we just return. Okay, and then we just do this depth search, root dot left. Okay, what's the parent of a root dot left?
Root.
Exactly, yeah. And what if I am going to traverse the right tree? Depth search,
Root.
yeah, wow. Okay, and then look, if parent, if it has a parent, then we get add a link. G root, right? G root dot append parent. And can you guess what's next? Right? And G what? Look, I have a root. I have a parent. So I'm adding a link. G root dot append parent. Adding this direction. So G parent dot append root, right? Okay. So and at the same time we should note what are the leaves. What are the leaf nodes? Okay, so I'm going to put a leaf node here. Leaves equals a set, okay? So what counts as a leaf node if it does not have any kids, right? Yeah? Now we just say if not root dot left and not root dot right? If it doesn't have any children, then the leaves dot add, okay? Because it does not have any duplicate numbers, we can use the set, yeah? Or we can use the list, it doesn't matter. Leaf dot add root dot value, okay? That's a leaf node. We might just be able to store the values instead because it's unique. So G root dot value, parent of value, root dot value, okay? So now we have this graph, now we do this breadth search. How do we implement the breadth search, by the way? Q, DQ, yeah? We talk about this, look. So 1, just a little bit summary, okay? 4, 5, 6, 7. So we have a Q, double NDQ. Q, first in, first out, right? And we use the DQ. Double NDQ means that we can append and pop in both sides. We can use the list in Python as a queue, right? As a queue. But the problem with the list is the operation on the left hand side is very expensive. It's linear. So we use the DQ to achieve O1 constant, the faster operation on both sides. Append, pop, append left, pop left. Okay? Yeah, we talk about this. When we want to do this operation on the left, we have to put the surface left. Otherwise, by default, it's on the right. So look, first of all, we put a root 1 in. We take everything out, right? Or take one node out. Put its kit is 2, 3. Yeah. So we can take everything out and append their kit, or we take one out. 2, its kit is 4, 5. Put it back to the queue. 3, its kit is 6, 7. Put it back to the queue. Okay. So every time we take one node out, or we take everything out, we push their kits back to the queue. There are two ways. Yeah? If we take everything out of the queue and then we append their kits back to the queue, that guarantees that at any time all the nodes in the queue belongs to the same level. Okay. Q equals DQ. At the beginning we put the K out, right? K is the target we want to find. K. Because we're converting to a graph, then we need to use the hash set to remember the nodes we visited, right? Usually for the depth search, breadth search, on a tree, we don't need to have this hash table to remember the nodes. We're only traveling from the parent to the kid. We don't go back, right? But after we convert it to a graph, we can go both ways, right? So for example, 1 go to 2, and 2 go to 1. 1 go to 2, 2 go to 1. We don't want that, right? It's a waste of time just to do the cycles. So to avoid that, we use the notebook to put down the nodes we have visited in a notebook in a hash set, okay? So scene equals set visited, while q, okay, then we current equals q dot pop left. If the current is in the list, right? If we found the list node, we just return current. Then we just find out what its next node connected to it. So for n in G current. But before we append it back to the queue, we need to find out have we visited, right? So if n in scene, or if n not in scene, then scene dot add n and then q dot append. When we put it back to the queue, we need to remember the node we are visiting. So let's take a look at this time complexity. For converting the tree to the graph, we need to visit all the nodes, obviously. So each node visited once. On time here. On space, this is we're using this dictionary, right? How many edges for a binary tree? The maximum. Look, if there are 3 nodes, how many edges? 2, right? Yeah? For the tree, because we can't put it, yeah? Then this is the maximum number of edges for 1, 2, 3, 4, 5, 6, 7 nodes, right? So how many edges? 1, 2, 3, 4, 5, 6. So if there are n nodes, there are n minus 1 edges, right? The space complexity for storing a tree as a graph is also linear, right? Because it's a tree, it's not a complex graph. For a graph, if it's not a tree, for n nodes, how many edges? There are 4 nodes, how many edges? The complete graph, okay? I can put, look, how many nodes? How many edges? 1, 2, 3, 4, 5, 6 edges, right? So every time I put another node, I can have n minus 1 edges. Okay, let me just put this in the table, right? So 1 node, 0 edges. 2 nodes, 1 edges. 3 nodes, 3 nodes. 3 nodes, 3 edges. 4 nodes, how many edges? 6 edges, right? 5 nodes, 10 edges. Look, do you see this keep going? 15 edges, right? Plus 2, plus 3, plus 4, plus 5. Okay? So next node is what? 7 nodes is 21 edges. How do we get this number? 1 plus 2 plus 3 plus 4 plus till n minus 1, right? So this is the formula. So n minus 1 plus 1 times n minus 1 divided by 2. Okay, so look, we got the square, right? The space complexity will be on squared, right? But for the tree is on, because for the tree, we don't have cycles. Coming back to this, for the breadth search, obviously on space, on time, right? On space scene, okay. Yeah, I talked a little bit too much today, okay? Okay, so what have you learned today? What's the problem and how do we solve it? And how many steps are we solving it? Come on, the last question, come on. Guys?
We learned
What's the problem?
tree.
Yeah, we have a tree. What are we doing with the tree?
Closest to leaf.
Yeah, we have given, okay, so we're given a binary tree with the unique numbers. And we also given a node, k. We want to find out the closest leaf node to k. And how do we solve it? First of all, we need to convert the tree into a graph. And then we do this breadth search on the from the node. And then we can find out, we can stop once we found out the leaf node, because that's the closest using the breadth search, okay? Yeah, for a breadth search to work, the edges is the weight is uniform, is all 1, right? So it's the cost of traveling from one node to another in the graph is 1. It's all equal. So that's why we can apply the breadth search to attain the shortest distance from the node to the leaf. Okay. Okay, the time space complexity is on, because we're using the breadth search, and we're using the depth search to traverse the tree to convert the tree into the graph, and that's going to take on, because all the nodes are visited exactly once. And then similar for the breadth search, yeah, in worst case all the nodes will be visited exactly once. Okay, that's it for today. Bye bye. Bye bye.